This is Professor Holman, and so this isn't too weird. I will show you that it is me, although maybe that was even weirder. Anyway, we are going to be talking about the synthesis that you're going to be doing on these lovely Cobalt-3 complexes you'll be creating, these two enantiomers. And what I have right now is it's actually a link that is on WISE. So you go within the folder, the Cobalt experiment folder, and there is a link there to this awesome website. It's University of Liverpool, and they have a bunch of structures on there that are 3D and JMOL. So here what I've done is I've moved the cobalt, this is the tris ethylene diamine cobalt-3 complex, and I have it so it's pretty much rotating around the C3 axis that's coming down here. So this has this propeller shape, but I also wanted to show you the perpendicular C2 axis. So if we move this and have one of these bidentate ligands sticking straight up like this, and as it rotates, you can see right here, that's that C2 axis that it is rotating around there as well. So I won't give away the point group, but you'll be able to figure it out, I'm sure. All right, so we're going to talk a little bit about the procedure as well as some of the aspects that I want to point out to you. So as you know, you'll be synthesizing these enantiomers of these two complexes. So this particular one happens to be the lambda form. This is the delta form. Those designations of lambda and delta actually, interestingly enough, do not necessarily always coincide in the same way to whether or not it is the positive enantiomer or negative enantiomer. That's just one of those things that was determined experimentally as people synthesized compounds, got X-ray structures of them, and then also the optical activity. But in any case, we're not going to be talking about the delta lambda aspect of it, but rather the plus minus optical activity that will tie in with what you will be doing experimentally with the polarimeter. So I did want to say a few things about the synthesis itself. So you've gone through, presumably, the pre-lab assignment and have looked at these major steps. And so we have this first one where you are starting out with this cobalt sulfate and adding your ligands, your ethylene diamine, the shorthand for that is just EN. And you are also carrying out an oxidation of the cobalt center with this concentrated hydrogen peroxide. And all three of these are pretty toxic. So, or definitely worth noting what their hazards are. So we have made those available to you. Another thing about the cobalt compound is that not only is it hazardous to you, but also to aquatic life. So that is definitely not something we want to be putting down the drain. Ethylene diamine is a pretty strong base, so you do want to be careful with that. There are other hazards associated with that. And then we have a very strong oxidant because this is 30% hydrogen peroxide, 10 times more concentrated than what you can buy over the counter. So we do want you to be very careful. You will be wearing gloves the whole entire, every day you're doing the synthesis. That is very important. So you'll be creating this racemic mixture at first, and I wanted to then point out that in the next step, and by the way, these are straight from your lab manual. So what I really though wanted to go to was these are the details of A, but that when we go to step B, so this is where you are going to then be adding the barium tartrate. So tartrate is also optically active, and that is going to be bonding to each one of those isomers in a different way. And a really wonderful driving force for this reaction is that it is forming a solid. So we have a precipitate forming. This is not your product. In fact, this is the opposite of the product because you want to get rid of all the barium sulfate that you can. This is not easy. This is where I want you to be very careful as you are following that filtration step. And it does say in the manual that you might have to do it more than once. It might say twice, but I want you to keep in mind that it could even be more than twice. You will want to maximize your chances of getting good yield, and you will do that by getting rid of all this barium sulfate. The barium sulfate is a nice and silky, is the way I describe it, silky solid, as opposed to the cobalt complexes. These cobalt complexes are a lot more chunky and crystalline. And so that's really the best way to distinguish between these two solids, because this barium sulfate, even though it's white, actually gets stained by some of the cobalt compounds getting trapped in the crystal structure of that. So just taking care at that step for sure. Okay, so as we follow down this synthetic procedure again, I just wrote out here again what I just said. Removing it, it's a colorless solid but gets stained. How to tell the difference? Look at the consistency of those compounds. All right, and then you get to separate the two enantiomers from each other. And the reason why this is even possible is that this tartrate compound, the tartrate anion, is actually 2-, but it is optically active. And the way it interacts with each one of these cobalt cations is that when it is forming a complex as the counterion with the positive cobalt compound, it makes a solid, and it is less soluble than when tartrate, and the plus tartrate, is interacting with the negative enantiomer of the cobalt compound. And so therefore it stays in solution, the negative enantiomer with the tartrate, whereas you get a precipitate with the positive. So this right here, this is the key to separating out those two enantiomers, is how they interact with that plus tartrate anion. All right, so at that point, you will then go down each separate line. So you will want to, of course, remove the tartrate, because that no longer, it has served its purpose, no longer useful. And in the end, you want to just get this cobalt, this tris ethylene diamine cobalt 3 iodine product. And so to get the plus enantiomer of this, you will then carry out, this is essentially, I think of this as a purification step, where you are getting rid of the tartrate with these steps with the sodium iodide. You need a little bit of base for that to happen, and ammonia does the trick there. And then once you get your product here, you cool it down and you will get a lovely product, I promise. Well, maybe I don't promise, but it is very likely that you will, and it'll be very cool when you do. All right, and then the other steps, so that negative enantiomer that stays in the filtrate because it's less soluble than the positive enantiomer with tartrate. With that one, you will also want to get rid of the tartrate, and very similarly, so very similar steps, you'll be adding sodium iodide, and along with some ammonia, that will be extracting the tartrate from that, and then you can isolate the negative enantiomer, minus enantiomer of the tris ethylene diamine cobalt 3 iodide. And again, you'll cool it and get some beautiful crystals out of that. You will notice that here is a water of hydration, and that is trapped in the crystal structure. That is very common and nothing to be concerned about. We do have, also just want to point out, there are often with syntheses washing steps, and so washing with this this salty water, essentially with the sodium iodide salt, as well as water, ethanol, and acetone. And this last step with acetone really helps to dry out your crystalline product in the end, and so that you can get your mass that is hopefully does not have any extra water besides any that are trapped in the crystal structure. All right, so wanted to again remind you, you've got these lovely two enantiomers that you'll be separating, and you have worked hard to synthesize them, but of course you need to prove to yourself, to get as much evidence as you can, is probably a better way to say it, that you did indeed synthesize these compounds and successfully separated them from each other. So you'll be then carrying out the Characterization steps. All right, did you prepare the one you intended? And the first steps will be to do structural characterization. So you will be carrying out proton NMR spectroscopy, as well as FTIR and optical rotation. And so this is where you have your, let's see. Yeah, I wanted to show this structure. So NMR, you will be able to look at the protons that are on the ethylene diamine, and that should hopefully give you an idea of the chemical shift and if it does correspond to those that are known for these compounds that have been reported in literature. FTIR. Here you're looking at vibrational spectroscopy. And so this will give you a chance to look at the various vibrational modes with, for example, the amine stretches, the cobalt, nitrogen stretches, and things like that that are relevant, that are indicative that you did indeed synthesize your compound. And then, of course, optical rotation, that's going to give you an idea of how well you separated those two enantiomers from each other. Okay, beyond structural characterization, you will also want to carry out electronic characterization. And what I mean by that is that with UV-Vis spectroscopy, as well as magnetic susceptibility, you can get some more information about the electronic structure of the compound, meaning, especially because we're looking at transition metals, we'll focus on the d orbitals and the d electrons within those. So with UV-Vis, you can interrogate the magnitude of delta, and with magnetic susceptibility, you can then go on from there and infer whether or not you have a high spin complex or a low spin complex. And of course, you can tie that in with the magnitude of delta. So these are the things that you're going to want to be thinking about, not necessarily in the nitty-gritty of your synthesis, but as you do begin to do your characterization of these compounds. Now, the synthetic products are the Cobalt-3 complexes, but we want you to think about things like delta and how the oxidation state of cobalt will affect delta. And so that's why we will be having you compare your products with Cobalt-2 aquated Cobalt-2 complexes so that you can do a comparison of the oxidation state, as well as with the aqua complexes, you have water as the ligand, as opposed to the ethylene diamine complexes that have the ethylene diamine as a ligand. And so again, thinking about how the metal center and the ligands will both affect the magnitude of delta, and then tie that in with your results and in your worksheet report that we are providing for you. So here's a reminder about the Spectrochemical Series. And so thinking about this, thinking about your inorganic chemistry and where different ligands appear, how those affect the field, whether it's a weak field ligand, strong field ligand, how that affects delta, the magnitude of delta, and then how that will affect the wavelength of light that is absorbed in your UV-Vis spectrum. And taking a step further, how that would affect your magnetic susceptibility results. All right, well, let me know if you have any questions, and I am happy to help, and I hope you have a blast doing this lab. Bye.